All right, so for any math students who have learned past trigonometry, or formally a lot of times, a lot of colleges and universities refer to that as pre-calculus 2, then you are now ready to study about polar coordinates. Okay, and so it has a long history, and so anyone outside of my lecture here, you can start doing a web search for the historical the development of polar coordinates. But here this lecture allow me to just focus right on how we operate with polar coordinates and get used to that. And then later on in your later future courses, such as calculus and all the future courses, polar coordinates here have a very diverse applications into those courses there. Okay. And so now, here we go. Let's get to know polar coordinates right here. Polar coordinates. All right, so I'm going to erase the title here, and we are going to maximize the board space here to get to work on that. All right, so at this point, anyone is well familiar with how we put a point on the coordinates planes, just the usual, the traditional coordinate system with the x and the y axis. Okay, so let me quickly bring up an example. So let's look at what we have here in the traditional x and y coordinate system. The x is the horizontal axis, and the y is the vertical axis. The origin is right at the point where the two axes here cross each other. So as a convention that we have been knowing, as a convention that well known worldwide, then the origin here is conventionally the point 0, 0, meaning on the x-axis here it's 0 value on the x-axis right at that cross point right there. And then on the y-axis, on the vertical axis here, it's also the 0 y value. Okay, and we have seen that all over our algebra courses, and that came up with graphing and all that. But now, from back to the very basic idea, any point on this plane, either I put a point here, okay, or I put a point here, or I put a point here, and I put a point here, and of course here I have to bring in a couple old terms, right? The quadrants. This is first quadrant, second quadrant going counterclockwise. The first quadrant here, second quadrant, third quadrant, and fourth quadrant, all of those point anywhere on the whole plane right here. But now since we have the axes, the axis system here being placed on, then let's say for a point here, we express any point relative to the origin here, relative to the axes here with as a convention. See, x coordinates come first. So let's say this point here, I'm placing that there as a 1, 1, for example. So that means this point is seated, right, at a point where the x coordinate. So in traditional coordinate system, then the x coordinates means the horizontal coordinates, and we list the horizontal coordinates first. So that's everything you have already known right here. So 1 here means it's 1 on the x-axis horizontally, positive 1. So that means from the origin here, 0, 0, we're going to go out. We're going to imagine we go out to the right-hand side, or on the x-axis, positive 1. So positive is to the right-hand side. And then on the vertical axis, we also going to, that point is sitting at relative to the y-axis is 1. Okay. So on the y-axis or the vertical axis, then positive is going up and negative means going down. It makes sense that way. Okay. And so this is, so 1, 1 is the way. It's the way we represent this point. The point is just a physical spot. You gotta, now at this point, anyone learning in this video is mature enough, because as I said, you have already studied past trigonometry, so you have enough experience to look at graph right here. Okay, and so now a point itself is just a point. A point is just a physical point, like a physical location on a map like that. Okay, and now once we have a system of a coordinated system, then we can easily reference our point positions back to the origin and relative to the axes here. Okay, so for example, again, in this point here, I'm saying 1, 1, that means where this point is located at, where this point is positioned at, it's at one on the x-axis and relatively one on the y-axis. So together the two components here, the two values here, x and y makes up that point. Okay, so that's the point. And we can name that usually with the point with the letter A. All right, so this system right here, since these coordinates are relative to the two axes, where now one important thing about these two axes, they're perpendicular with each other. They're perpendicular with each other, and once we kind of trace out the coordinates right here, then we form into a rectangular picture. Okay, we form into a rectangular picture, and so this traditional form of representing any points using horizontal and vertical coordinates, we refer to this as in traditional term, and you must have seen this before as well. Okay. This is referred as, this point here is referred as rectangular. I mean, the way to represent is called a rectangular, using the rectangular coordinates. All right, that's one way of saying that, rectangular coordinates. Meaning, once we trace down, on the x-axis and trace over to the y-axis, we form into, and relative to the two axes, and with the origin here, we form a rectangle. All right. And so now, another way of saying this way of representing a point using horizontal and vertical coordinates is also known as, so rectangular coordinates is one way of saying it. It's also known as the Cartesian. Okay, the Cartesian coordinates. Okay. The Cartesian coordinates. So rectangular coordinates or Cartesian coordinates are essentially the same. All right, so that's just, like I said earlier, that's just one way, and it's the way we have been knowing it, how to represent a point, okay, on the plane here. And the plane is just the plane itself. Like a map is always just that map, and then the point is just that physical location. Once it's there, it's just there. Okay. So now allow me to, this is just a brief review of what it has been from what we know. So now the same point and even the same axes, the same axis system here. Now I'm gonna erase away. I'm gonna erase away these notes here, and I'm still gonna retain the point, but I'm not gonna write. Okay, we can still put the x and y axis here. That doesn't hurt. But I'm going to completely erase all of these coordinates right here. The point is still there, and we don't need to move the point, because I want to emphasize that the point is just that same point. But now instead of representing this point in terms of x coordinates and y coordinates as a pair right there, then here's another way. So let me just introduce that way, and then we're gonna formally introduce what that is. We're gonna formally introduce the idea right here, get to know the idea. But so as another way of seeing this, from any point we place, at any point we place on the plane right here, it will definitely make a distance to the origin. And that's why I said there's no need to erase the two axes here. But now, admittedly, and I will get more into that, admittedly, out of the two axes, the x-axis is more important. Okay, the y-axis is not as important. Okay, but now here's the origin, the 0, 0 points, right, in rectangular coordinates. But now just keep that as the origin. So now we call this origin here the pole. We treat the origin the pole. And so now if we call that point here, that origin here the pole, then any point on the plane, any point, whether you're putting that in quadrant 1, quadrant 2, quadrant 3, 4, and so on, any point will make a distance. That's what I'm saying again for sure, any point. So that same point here that was 1, 1 in rectangular coordinates, now that same point makes a distance. So that distance here, let's call that as the radius r. Okay, so r here for, so let's make a note. R here means radius. That's how we traditionally calling that, because it's a distance. Okay, so in formal math term we call it as a radius. So keep that in mind. So r is just the radius from where the point is down to the origin, back to the origin. Okay, and it's a distance. And then from from where that point is. So, and once we draw that radius, once we have drawn that actual distance right here, then that little segment connecting between the point and the origin will make an angle. But here's the thing, that very critically, very critical to understand that the angle is always referenced back to the positive x-axis. And so from where this angle is, then it will always make an angle theta going in a positive direction, from, an angle theta that's opening in from the x-axis. I shouldn't say in a positive direction or negative direction yet, because negative direction also accepted. But basically, angle theta is the angle that's being referenced, taking this x-axis, the positive x-axis, as the reference, as that reference side right here. Okay, and then we're gonna open up the angle theta. All right, so now that means here's the idea about polar coordinates right here. So that same point A can also be expressed as the point where it makes radius r, okay, from the pole. So that point is a point. So instead of saying, hey, that point is sitting at 1, 1, so that same point is at radius 1, at some radius r. I haven't calculated that radius yet, and we will get to that. Okay, so at that radius, at some radius r, in respect and with angle theta. Okay, so welcome aboard, welcome ladies and gentlemen. You are now looking at the polar coordinates representation, okay, or the representation of this same point but in polar coordinates. So this is what we refer as the polar. Okay, so now is the polar coordinates. All right, so the reason it's called polar coordinates because just being consistent with what I have explained earlier, we call this origin here the point, here being the pole. And so any point other than that pole right there will make a difference. We'll make a distance with that pole. And then the coordinates pair here is represented in terms of how much distance from the pole and how much angle at the pole right here, at the pole that being referenced away from the positive x-axis. And that's why both of the coordinates values are here are relative to that pole right there. And this is the reason why this representation style is called the polar coordinates. Okay, so it's a way, I have to emphasize that it's a way to represent the point, but see, I did not have to move the point at all. The point stays the same. It was that point 1, 1. Okay, but now instead of expressing that point as horizontal axis and vertical coordinates and horizontal coordinates, we're expressing that in terms of radius, how much radius it made with the pole and how much angle it made with the positive x-axis. And that's the point of what polar coordinates is all about. All right, so now that is all about the understanding of polar coordinates, and the rest is all about how we develop further understanding in terms of polar coordinates. All right, so right here at our very start of the journey right here, that point I initially put at, in rectangular coordinates, that point was at 1, 1. That was the rectangular coordinates. I put it there. It's 1 here, and it's 1 here, okay? On the y-axis. So now let's quickly find out, and you know enough, and of course there's still a whole journey of polar coordinates out there, so I'm only now specifically talking about this particular point right here. In rectangular coordinates, it was a 1, 1. All right, so the reason I said earlier in the video lesson here that this lesson is meant for students who have already learned past the trigonometry. Simply because once you have learned past trigonometry, that's including all the students in the calculus level and even up. Okay, then once you have learned past trigonometry, then you will understand. You will have a way to figure out how much distance and how much angle this is. All right, so this point is sitting at 1, 1 in rectangular coordinates. Okay, so this distance here, this vertical distance here is 1, and this horizontal distance is 1. Okay, so that means the radius is the hypotenuse of this triangular shape right here. So right here we have a right triangle, 90 degrees angle right there. So hypotenuse is this r. And so that's why in this case right here, we can see that quickly the radius in our case here is, according to the Pythagorean theorem, square of that hypotenuse, because radius is the hypotenuse in this triangle, x squared plus y squared. And we now know that r squared is, and each one of the x and y was 1 and 1, right? And so 1 squared plus 1 squared. We are now looking at r squared equals 2. And r squared equals 2 means r equals plus and minus square root of 2. But that, so here, it's an actual distance. It's an actual distance. So we're going to take the positive. Okay, so it's positive square root of 2. And yes, this point here is located at the point where it's made. So in polar coordinates, it's square root 2. That's the radius right there. That point is at radius 2. I mean radius square root 2. And then width angle, let's find out how much angle that is. Now, you don't have to bring back too much trigonometry understanding yet, because I want to save that for the later stuff. But this is just basic high school geometry can get you through right here. This triangle itself in the end is a 45, 45, 90 triangle, or it's a right isosceles triangle. And since the 90 degree angle is here, then this angle has to be a 45 degrees. Okay, so now there are two ways of communicating in terms of the angle right here. So, and as I said earlier, the angle is strictly measured in terms of how much opening out from the x-axis. The angle is being how much angle made from the positive x-axis out to that ray of the angle right there. And so now in degrees, and we have two interchangeable conventions right here. You can measure angles in degrees or in radians. So in degrees, this angle is at 45 degrees. That's one way of saying that. So this is our representation of the same points in polar coordinates. And the angle here is written in degrees. Okay? And then the same way right here, that same point, you can also say the same point A here is at radius square root 2, and the 45 degree angle. Now for students who have learned, this is like I said, this is meant for students who have learned past trigonometry. So for students who have learned past trigonometry, then 45 degree angle is well known as the pi over 4 angle. So this is still polar coordinates, but we are expressing the angle in radians. All right, so now, as I said earlier, welcome aboard. Now you know about what polar coordinates is all about. Okay, so it's just a way. The point is still that same point, but instead of representing that as in rectangular coordinates, we're representing things in terms of how much radius it makes. So, and critically important that you got to see that we list the radius first, and then we list the angle theta. And then for angle theta, we have two different ways. So it depends on every problem that you're working with. It all depends on the situation. So watch for those conventions in each problem you're doing, whether the problem is asking you to express your angle in degrees, or the problem is asking you to express your angles in radians right here. But now these are the two various forms, okay, of polar coordinates representation of your point. How much radius it made, that point, same point made from the pole, and how much angle it makes relative to the positive x-axis. Okay, and so now, and there are still more. This is just the very first introductory understanding. Okay, and so there are still a lot more right there into that. All right, and so now that's what it is about the polar coordinates. So let's now try to understand even further. So that same point right there, you can represent that as, so this is in degrees, this is square root of 2 and pi over 4. Okay, but so now, like back to what I was accidentally said earlier about positive direction or negative directions. When we are representing a point, in polar coordinates, we are allowed it. It's completely allowed it to express the angles as a negative angle as well. Okay, so now we have to connect what we understand, we have to connect what we're studying here with our past understanding about in trigonometry. So if we think of this, and the angle, the point is the point, okay? That same ray right there is just that same ray. All right, the same ray that's making this terminal point right here. If we're speaking strictly in terms of the trigonometric terms, then from where that terminal point is, right? We can see there are two ways of seeing the angles. You can see that as a positive angle, meaning from the x-axis. Here we go. We think of a counterclockwise, a positive rotation. But from the same angle, the same terminal side right here of the angle, we can also think about it's the same as having a negative or clockwise rotation. Okay, and so that means the same point being distance square root of 2. Okay, but you can also see this angle being the same as the angle negative 315 degrees in degrees, negative 315 degrees. If we're seeing that same angle with that terminal side, okay, as a negative rotation from the x-axis and have a negative rotation down up to that point right here, then it's a negative 315 degrees in degrees conversion. In degrees convention. And so, and the same way, the same point right here, we can also express that. Okay, that's why, you know, one point can have multiple. At this point, we can start drawing out a conclusion in either degrees or radians. We can have multiple representations in polar coordinates for one same point. Okay, so now in radians, it's square root 2 for the radius. That's how much radius the point has made. Okay, the point made with the pole, and then it's the negative 7 pi over 4 in radians. All right, so it's already two different representations. Now, either in degrees conventions or in radians conventions. But mainly how I see, you can list that same point as a positive angle or as a negative angle. So make a note of that right here. Angle theta, okay, is allowed to be negative. Okay, that's one thing for sure. One thing that's completely allowed. All right, and so now after being aware about theta is allowed it to be negative. Now, there's another shock right here. There's another shocking news right here. So, in the way how I have been explaining this radius right here is how much distance from the point A to the pole. From the point A to the pole. But here's a surprise. Here's a big surprise here. So, anyone has been knowing for years that distance cannot be negative. Distance cannot be negative. And that's why even in that little calculation earlier, I chose a positive square root of 2. Even though instead, technically, when you take square root of both sides, when you had earlier r squared equals 2, when you could have done, you had two expression, r equals plus and minus square root 2, like that. Okay, just that's the algebraic, the understanding, like that. And I chose square root 2 because my explanation back then was r was a distance, so we chose a positive 2. But now I'm talking about the way to represent. Okay, I'm talking about the way to represent. Then here's the thing. The shocking news I'm about to announce is as following. All right. So now let me erase to make some more space for myself right here. Now, the shocking news I'm about to say is radius, okay, can also be negative. It's also allowed it. Radius can also be negative. Okay, radius can also be negative. Okay, so what a shocking news. So how do we represent negative radius? All right, so here's how I'm seeing it. So let me now swing to the other board and construct a new figure. All right, so in the axis system, now I call this the pole right here. Okay, and of course in rectangular coordinates the pole is at 0, 0, but now we can just see that it's the pole. Okay, and so here's how I see it. So when I said earlier radius is allowed it to be negative, or radius can also be negative, and when I said also, that means because I already explained earlier that angle can be negative. Okay, and so now the same with radius. Radius can also, surprisingly for polar coordinates representation, we can also use negative radius. So here's how we're doing it. Let's say I'm going to put up how about a negative square root 2 comma pi over 4. Let's do a quick little example over here, and we will get to formal examples where we formally plot these points right here in polar coordinates. But let's say now you are given a point in polar coordinates. Let's call this point B right here, negative square root 2 comma pi over 4. And so now we know that this point is in polar coordinates convention, in polar coordinates representation. So you got to start getting used to this. This first value is radius, and this second value right here is the angle theta. And so right now, in the way how I see it, it's already expressed, it's given in radians. Okay? But in radians or in degrees, it's not too important. We should be able to work fluently on both conventions of the angle. But now here I notice we have a negative radius. And so throughout this quick little example, allow me to start showing the formal way, at least how I have been personally doing it throughout my years of doing math and teaching math right here, of how I have been doing an actual hand sketch of a polar coordinates point, how I can plot a polar coordinates point. Now it's a little bit counterintuitive, but the radius is listed first and then the angle. But for me, I have been personally finding it easier to. This is our x-axis, so I'm going to be looking at the angle first. It's a positive angle, so I'm going to think about a rotation. So from here, a rotation to, it's a positive. So let's do a positive rotation. So we rotate to 45 degrees. So here's my 45 degrees, or my entire ray. Think about the terminal side of an angle. It's stopping right at pi over 4. This is the angle pi over 4 in the positive rotation. That's exactly that terminal side. But now on this terminal side, on this ray that I'm dotting with red ink right here, we're going to look for a radius not positive 2, negative square root 2. Not positive square root 2, negative square root 2. So here's how I'm seeing. Let's say if this much, think about there's a 1 here, then if we put the points right here, then this is positive square root 2. That's not the answer we're looking for. This is positive square root 2. So here, this is how we put negative square root 2 right here. That same terminal side, I'm going to think about. See, it's opening up at pi over 4. All right, but the negative means the exact same distance. But I'm going to put that on the opposite side right there. On the opposite side. On the same ray right there. Now on the same line right there. Okay, on that same dotted line right here. Pi over 4 angle is from here. Is here, opening up from the x-axis in a positive direction at the amount of pi over 4. In terms of angles. And then it would have been this point if it was a positive square root 2, but now being a negative square root 2 distance, or negative square root of 2 radius, then I'm going to put that point actually down here. All right, so this point right here, so now I can formally make solid line right here. So this point right here, ladies and gentlemen, the real point is, the point B is here. Now I put that in red ink, being negative square root 2 comma pi over 4. All right, so the work that I was showing, hopefully anyone viewing this video is catching the steps. First, we look for the angle, whatever it's indicated here for the angle. We look for the angle, and then in the worst case, if the radius is a negative radius, from where the angle is, we're gonna look for tentatively from where that angle is, we're trying to look for that length, that radius, but that was the positive radius. But now, since the problem was looking for negative radius, from where that positive radius supposedly there, we're going to take the opposite end right there. Okay, and that's how we come up with the point involving negative radius right there. All right, and so that's how things work out right there. So that's it's a shocking news that negative radius is allowed it. Okay, negative radius is also allowed it, but that's the way how we draw it and how we represent a point with negative radius. And so now, back to what I said earlier. So now I'm going to get back on this picture over here. As we have already agreed and been through. And the pole is now here. I think I can erase that. Okay. Then pi over 4 is this angle. Then about right there, this point is negative square root 2, comma, pi over 4. That same point there. And with that point, I named that B. So now allow me to come back to what I said earlier, that one same point can have can have many or multiple representations in polar coordinates. This is what I meant earlier over here. I mean, you have already seen, the same point here, but you can express that, and with the same positive radius, you can express that as either a positive angle opening up or a negative angle opening up. Okay? And I'm still talking about the same point right here. I put in that point B, it's just for extra clarification. But now this same point A right here, we also have our choice to think about. Okay? So think about what if we, in a positive angle, we can think about, we go in as a positive angle, we go all the way down to that ray in red right here, but then take the negative radius. So if we're opening an angle from the x-axis in a positive direction all the way to that red terminal side right there, then we're looking at that angle there being a positive 5 pi over 4. That's a positive angle in a positive rotation to land at that point. But now I'm not looking at this B point. I'm looking at this, because once we're looking at that big opening angle, right, and then the negative radius is going to land you back into that point A. So negative square root 2 is negative square root 2 comma 5 pi over 4 is another representation of the same point A in polar coordinates. All right, and there's still more. There's still another one. So what about, I can see this as a, I can see this as a negative angle with a rotation from the x-axis rotating in a negative direction to that red terminal side right here. And then if it was a positive length, positive radius, then it should be this side right here, but now it's negative radius, so it lands back into that other point. It flips back into that other point A right here. So now I can see this same point as, we can go a negative 3 pi over 4. Okay, 3 pi over 4. That's for the angle, because like I said, this is my own personal experience. So that I'm teaching along with blending in my personal experience, how I have been doing it and teaching it. Okay, so hopefully it could be successful for anyone learning from this. But otherwise, that's just my style. But in the end, the point I'm trying to make now is that the one same point, we can have multiple representations in polar coordinates. So in how I see it, this angle, we can think about opening up a negative 3 pi over 4 angle. And then on that ray right there, on that terminal side, we're going to flip, so with a negative radius. So negative square root 2. All right, that is the same point here for that same point A at 1, 1. All right, and so that's what it is in terms of, now we really know enough, okay, about how to operate with all of the polar coordinate representations, or all representations in polar coordinates of any point, of any given point. So now the last thing I need to emphasize before we start heading out to some further concept, and as well as getting into some examples, that I have to emphasize again, a point is just a point. representing that point in rectangular coordinates or representing that point in polar coordinates. It's just a way to represent, but the point is just that same point. Okay, so here we have the pole, and in the polar coordinates we have the pole, and everything is measured in terms of how much radius away from the pole and how much angle at the pole opening away, either in a positive direction or negative direction from the positive x-axis. That's all it is. I mean, that's all it is that defines the polar coordinates convention like that. All right. All right, so now we are ready for example 1, where it's a very basic example. We just get used to plotting, right? Get used to plotting in the polar coordinates. I mean points. We plotting points on the plane, but the points are given in polar coordinates. Okay, the points are given to us here. They are represented in polar coordinates. So let's look at example 1. All right, and so plot the following points. Okay, or just the following point, and we're gonna be given different points. Yeah. So we want to plot the following point in polar coordinates. All right. And so the point is given to us, and it comes as, the point comes in polar coordinates convention. Like that, we just want to read that information and be able to place that point successfully on the graphing system. That's what matters. All right, so here we go. First point, and before we really get into this example and get any further into the problem, allow me to start introducing how we can also do this with decimals here. So decimals, I found that even though you also can use any of your standard graphing calculator that includes the TI 8384 or the HP graphing calculators or even the Casio's graphing calculators, but among all of those technologies out there, I prefer using decimals because the graphical system, the graphics is showing me the best graphs like that. Okay, and it's free. You don't have to spend a dollar or even a cent to buy the machines like that, and it has really nice features. So I will use decimal for most of my demonstrations here, and then at some point I will also introduce some actual use of decimals. Okay, because it has some good advantage for your learning in polar coordinates. So back to this example 1 right here. Part A, you are simply given a point as following: 5, comma, pi over 3. All right, so let's get used with that. This is a point, but it's not expressed as this point is not represented in rectangular coordinates. This point is represented in polar coordinates. So this is radius, angle. Radius from the pole, an angle made from the axis on the x-axis, right? The polar angle that's made from opens away from the positive x-axis, and the angle itself, observe that it's a positive angle. All right, so now I'm only gonna do a quick sketch here, and then I will swing over to decimals for the precise place where we plot that. Okay, so it's a positive angle, so the x-axis is here, the positive x-axis is here. So think about, and this is our pole, okay, and we don't even have to place down 0, 0 anymore. I just call this is the pole, okay? That's the pole. So from where the pole is, think about there's an angle rotating in a positive direction. All right, so pi over 3 is about an angle like that, and that's why I'm very upscale, and eventually I'm gonna switch over to decimals to have the precise graph. So the terminal side of my angle has to be somewhere here. That's about the angle pi over 3, positive pi over 3. And then on that angle right there, on that side indicating the angle, now I'm going to look for about 5. So my scale right here, 1, 2, 3, okay, 4 and 5 right here, and then make a circle right here. So that 0.5 is about right there. Okay, so this point right here is at radius or equals 5. If the scale on the x-axis, each of these little space right here is a 1. So 1, 2, 3, 4, and 5 there. And that's why I said I'm quite upscale right here. and eventually I'm going to switch to decimal to have the exact look at the graph. Okay, so that's how I place down the 5 comma pi over 3. All right, so really let's now switch over to decimals and find out right there. All right, so here is our famous decimal screen. So now decimal does have a powerful graphing feature. I mean, decimal has a very nice graphics and powerful feature right here. Decimal allows you to switch between the polar coordinates as you are currently seeing right here, or rectangular coordinates. So all we do, so for anyone who's learning to use decimals as well, we click on that button right here that says that has title graph settings. Click on that, and that button gives us the choice to switch between. See, this is rectangular grid right here. Okay, the traditional rectangular grid, or we switch over to using polar coordinates. So really, it's the same axis system. You can notice these numerical labels. They say the same as we switch to different style of coordinates, but these scaling stays exactly the same. So like, for example, that 2 right here stays the same. So when we switch over to polar coordinates, it stays the same too, because it's just how much space on the x-axis. So this much space right here is a radius 2 right there, and the pole is right here. Okay, but so now once we have turned our graph to polar coordinates mode right here, then at radius 5 and with the angle pi over 3, okay, you don't see any change much. But so now let's look at the graph right here. See, the graph with decimals is giving us these minor grid lines right here that's right on those special angles. So this is a pi over 12. See that ray right here, that's very light gray right there. Okay, so pi over 12, 2 pi over 12, which is a pi over 6, 3 pi over 12, which is the same as a pi over 4 right here in the 45 degrees angle, and then pi over 3 is right here. So we have that ray right there. So now on this ray, I'm expecting to put a point at 5. So see, this is how much radius: 1, 2, 3, 4, 5. So at the angle, I'm expecting a point right there. So in a positive, a positive angle, pi over 3 is this ray, and then we come out, we leave the pole at a distance 5. So 5 is right there. So now let me put the point on. All right, so that point stays consistent with what I was expecting. All right, and so that's how we're plotting that using decimals right here. So in case anyone would like to know how to use decimals, then allow me to actually show the actual setup of decimals right here. So now you're in decimals. On the left-hand side panel right here, this is where you enter all the command entry. Now, decimal, any technology does have a weakness. Okay, so for decimals right here, I have to warn anyone, if you're using decimal to make your polar coordinates plots right here, or to plot your polar coordinates points, then be careful that do not use theta and do not use a lowercase letter r. So traditionally on handwritten version, we use lowercase letter r for radius, and we use theta for the angle. But then for decimals, if you're using those decimals, we immediately use those for the polar graphs, which we will learn that later. So don't use those. Stay away from those. We can use any other variable's name for theta and any other variable's name for radius, except lowercase r and except theta. So here for a angle theta, we can use, or how about for radius? I can use capital R. Surprisingly, it will do the trick. So capital R being 5 as the problem indicating here. So R equals 5. It's not a complete point yet, so that's why we see nothing here. Okay, and again, I'm staying right here with that particular problem. The very first problem, I try to give in a lot of detailed explanations. So now I'm showing along the way how we use decimals in case anyone want to run decimals. Because I found out that with the other most of the graphing calculators on the market are not able to handle this job where you're plotting it. So if you're not using decimals, then you have to do these things as a hand sketch. So that could take away some time right here. So it may be valuable that you learn a little bit of decimals skill right there. Okay, that it's free. It's a free resource and quite powerful. All right, so this is the point we're plotting. But now with decimals, radius 5, I have already entered. Radius 5 now. So just as I said, stay away from lowercase r. So here positive capital R is completely just fine. We don't see the point yet. So now angle theta, don't type the word theta because that's already reserved by decimals here, and that's why you can see that there's also this critical exclamation mark right here indicating that decimal is about to reject your typing here. So we can type a phi as another name, or t or s or whatever. Okay, you can type a t right here for angle. And now I'm going to say t equal, okay, and there's a pi over 3. That's the angle right there. Okay, so decimal unfortunately doesn't have a way to show this in exact precision like that. So we just have to live with that display, but it shouldn't change any of our results. All right, so now we have t equals pi over 3 and then r equals 5 right there. So now I'm going to put the point. I will come back and explain the math later, but to actually display the point, this is what we have to do. To actually display the point, this is what we need to do. I'm going to open a point. The x coordinates is r times cosine of t, okay, and then the y coordinates is r times sine of t, okay. And so now look at that point just popped out right now. But now in this way, even though I create that point, the setting for the point looks like it was in rectangular coordinates. But now when the point is plotted, and it's going right with that polar coordinates convention. And so, and I can change that setting a little bit right there. Okay, and so now that point right now is right at the angle pi over 3, and then at positive radius 5. And then after we have set up this template right here, then we will never have to go back and change this command line if we're looking at another point. So let's head out to part B right here. Let's head out to part B. So let's now look at another point, and now I'm going to deliver a quick off-scale hand sketch, and then we're going to switch over to decimal to see how decimal is giving us a precise picture right there. Okay, and so in part B, let's look at that point at 2, 5 pi over 4. Okay, 2, 5 pi over 4. So as an off-scale, in my off-scale hand sketch version, the pole is here, okay, x-axis is here. So in my personal experience, I'm going to look for the angles first. So the angle is a positive 5 pi over 4. So from this x-axis, we're going to rotate in a positive direction to 5 pi over 4. 5 pi over 4 is this rotation to reach down here. That's my angle 5 pi over 4, positive 5 pi over 4. And then from here, I'm going to look for radius 2. So if we set our scale 1 and 2 here, then that much space, 1 and 2, is going to create my point down here. Okay, so this point right here is 2, 5 pi over 4. And that's the point right there. It's right at that. See, and like I said, please do not blame me or be upset at me when my picture here is a little off scale, because I'm only a human being. Okay, and so now switching over to decimals. All right, so now on decimals, we can have, see, the angle here, or actually the radius here is 2, okay, and the angle is at 5, or I can delete this completely, it's out completely, okay, 5 pi over 4. All right, so just as expected. Now let me zoom it in a little bit so that anyone can see a little better. But see, with these grids right here, so 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which makes a pi, and 5 pi over 4 is right here. So the decimal placed the point on the correct angle opening already. So that with that, and then here with radius 2 coming out from the pole, so 1, 2. So right there we had a point, which is making it consistent, perfectly consistent with what we have had earlier. Okay, and so again, to have a closer and clear view on that, let me switch over to a closer zoom right here. All right, so now I zoomed in so that we only see the graphing space. So this is exactly where the point is. See the opening up of the angle, Right? 5 pi over 4 is that angle going in positive direction that lands down right here. All right, and then add radius 2. All right, and I can even zoom in a little more. All right, so that's how it works like that. And now let's look at another point given. Okay, so now things can start speeding up the process a little bit. We can start picking up pace a little bit. And so at this third one right here, let's look at, how about a negative radius, negative 3. And like I said, negative radius is completely okay, okay, as far as in the way we represent a point in polar coordinates. Okay, so it's not really, it doesn't really mean that we have a negative radius. It's just negative radius is a way to represent, okay, a point. So now 5 pi over 6. All right, so again, with my hand sketch version, we're going to look for the angle first. So 5 pi over 6. So this pi right here is about 6 pi over 6. So 5 pi over 6 is about right here. Okay, so pi is about 6 pi over 6. So 5 pi over 6 is right about that. So here's our line. Okay, that's indicate the angle 5 pi over 6, positive 5 pi over 6. But now on that angle, let's look for this is not the actual point, because it's that would be the point if it was a positive 3, but now we're looking at the negative 3. So I explained earlier before we got into this example. So now from that point there, tan theta 3, okay, 1, 2, 3, okay, then I'm going to have to take the exact opposite point down here. There you go. So this point right here is a minus 3 comma 5 pi over 6. That's just how it is right there. All right, so it's a hand sketch that I'm doing. So on decimals, all right, so let's switch over to decimals here. So again, we're going to look for 5 pi over 6, which is right here, okay, and decimal has a much better precision for us right there. Okay, so right here is 5 pi over 6. All right, so here's the point. There we go, just like that point that agrees with what we had on the board earlier. See, so 5 pi over 6 from the x-axis, we go 5 pi over 6, which is landing right here for that terminal side. But then for radius being negative 3, we're going to swing down this way. And that's to indicate negative 3, but at angle 5 pi over 6. So that's the point that we're looking at, like that. And now for the version of that shows the complete screen with decimals here, then you can see that, negative being a negative radius, I use a capital R equals negative 3, and then with the angle theta, I call that t equals 5 pi over 6, and this is the way how you can construct your own graph here, and I will come back and explain the reason why I have to go with this. It's a limitation with decimals that we will overcome with that later. But for now, let's just focus on the graph right here. So as long as you provide, once you've had that, we will never have to change this command line right here. But all we have to do is change the different values here for radius and for angle theta. And that gets us the correct point right here. And so this point, once again, is at radius 3. The angle was supposedly 5 pi over 6, which is right here. But then we take the negative radius, so that's why it lands down there. All right, so now let's look at another one. So question D right here. And now starting with question D, I don't think I any longer have to do the hand sketch version here, and let's directly get to decimals. So the point in D right here is negative 5 comma 4 pi over 3. Very similar to that point we plotted in part C earlier. Okay, so that's why I said we don't really need to do the hand sketch here on the board anymore. So with that point, I'm going to switch over to decimals. All right, so decimal is still having my other point right there. So now with the radius here being negative 5, I'm going to change this to negative 5. Okay, and then with this angle right here, I'm going to change this to 4 pi over 3. Okay. And so now that is 4 pi over 3. All right, so in the closer view right here. 4 pi over 3 is this angle. Right here, down here, is the angle 4 pi over 3. Okay, but now if we are looking at, if it was a positive 5, then the point would be right here. Okay, but now in our problem, it's actually negative 5. So from where the terminal side of the angle 4 pi over 3 is, as I said, in my experience, it's always best. It has always been best for me to look for angle first. So I open up 4 pi over 3 in a positive rotation. And then the opposite of that, because it's negative 5, so I'm going to put the point is actually down back this way, somewhere there to expect. So now let's look at the point. There we go. So now that point is here. Okay, so it's at the angle opening up in a positive direction, 4 pi over 3. Okay, that's why my mouse cursor has been moving in that way. And then the point is switched over, the point at the radius is negative 5. That's why the point is turned the other way, opposite side right there. All right, and now let's switch to the actual version of decimal so that we can see how we can construct it ourselves like that. So negative 5 is the radius, and I'm going to change this to angle 4 pi. So negative 5 is radius, okay, and I'm going to change this to the angle 4 pi over 3. All right, so that's the angle, and so now our point has been changed. Okay, so the radius is a little too far for the screen, so let me now zoom it out a little further out. And now it will show the point. All right, so the point is now right here. All right, and I can even zoom it out a little more so that it can see a little better. All right, so right there. All right, so now the last point in our example. And again, I don't think I need to create a hand sketch here anymore. Let's once I have a point here, I'm going to show two versions on decimals, a close-up version and then the actual version how we're doing it with decimals. So part E right here, another point. How about positive 3 but negative pi over 3 angle? Positive 3 and negative pi over 3 angle. All right, so now on decimals, all right, with the close-up version right here, then we're thinking about the angle as being a negative angle this time. So from the x-axis, the positive x-axis, we're going to go clockwise. Okay, and so pi over 3 angle is about right here. I mean, negative pi over 3 angle is about right here where the terminal side lands right here, aligned with 5 pi over 3. Okay, but 5 pi over 3 is written in positive rotation. Now we're looking at negative rotation, then it's this same angle right here has to be a negative pi over 3. So at negative pi over 3, I'm going to look for this. I'm going to look for radius 3. So on this terminal side of the angle, we're going to look for radius 3, which should land us a point right here. All right, so now let's put the point on. All right, so that point is right there, and it reads it reads 3 comma negative pi over 3. And now I'm going to switch over to the other decimals. All right, so now in a more complete view where it shows how we can do the problem ourselves, the radius is 3. We can just type in 3, and now it's a negative pi over 3. So I'm going to change that angle theta, or now I call it t with decimals, minus. All right, so now as soon as we change those two values, we have the correct point being placed right here. All right, and so now with that point right there, once again, let's clarify it. It's a negative angle. If we want to see it that way, it's a negative angle that's open up from the x-axis, being negative pi over 3, and then it's at radius 3 away. See, 1, 2, and 3 at radius 3 away from the pole right here. All right, so that's how we're done with example 1 right here, and let's now look a little further into the understanding of polar coordinates. Okay, and we're gonna head ourselves after some further look into the polar coordinates. We're gonna head into example 2. Okay. All right, so now I have mentioned this, and now I want to emphasize one more time, but polar coordinates or rectangular coordinates is only a way to represent a point. So those two together, they're just different ways to represent a point. But in the end, the point itself is just a point. So now the axes are here. You can call we can call that point here the origin or the pole. It's a different way how we want to say it. And now any point has coordinates x and y in rectangular coordinates. But then that same point right here, but that same point can make radius r with some angle theta from the positive x-axis right here. That's opening in either positive direction or negative direction. And so in the end, rectangular coordinates or polar coordinates, okay, or common theta, two different ways. Those are just different ways to represent your points, your particular point, for actual physical points. And so now we have to learn a way, because there is now in the end a close relationship to convert between rectangular coordinates and polar coordinates right here. Okay? And so you actually have seen that in my Desmos demonstration, and now it's time for me to also explain. And this is where you have to bring in more of your trigonometry understanding. So here's how I'm seeing it. If your point is represented in polar coordinates where we have radius r here and the angle theta, it doesn't matter positive, negative direction, but so how is that related with y coordinates and x coordinates? So x coordinates is here and y coordinates is here. Okay? So how is that all related? So now you can see that as from our trigonometry understanding, then the x coordinates right here in this triangle, if the angle theta is here, then in this triangle, this x coordinates is the adjacent side relative to that angle theta. So in that way, x over the radius from our understanding in trigonometry, then it will equal to cosine of theta. This is our understanding from trigonometry. Allow me to not go too far back into trigonometry, but x over r is famously known from trigonometry, that equals cosine theta, where theta is located like that. Okay, it's defined like that. And then similarly, our y coordinates, the opposite side, opposite from that angle theta. This is hypotenuse, this is adjacent, that's opposite. So the y coordinate is the opposite. So y coordinates divided by the radius will equals, and we saw that as some of our definitions, or at least the consequences of the definitions of sine and cosine function back in trigonometry. So this is y over r equals sine theta. So we knew both of these from our past understanding in trigonometry. And so now from that way right here, we can consequently multiply on this equation right here, we can multiply r from both sides. So that leaves me x equals r times cosine theta. Okay, but what good is this doing for us? You see, x as a variable representing the horizontal coordinates in rectangular coordinates of our point. But x now equals r times cosine theta. R is the radius of the point, and cosine of theta. So theta is how much angle opening up, and we can always calculate cosine using a calculator. Or if it's one of the common point on the unit circle, we can easily find it out from the unit circle, cosine of theta. And so now this is actually a way to convert from to convert from a point that's having known polar coordinates representation, and we convert that. At least we know a way to find the x coordinates of our point in the rectangular coordinate system. Okay, and so similarly, if we have found a way to calculate our x coordinates in the rectangular coordinate system, then we can also do the similar thing for the y coordinates. So if y over r equals sine theta, then we can have y equals r times sine theta. We simply just multiply r to both sides of that equation. And so times sine theta equals y. But this y value, it's the vertical coordinates. It's the vertical coordinates of our same point. okay, in the rectangular coordinates. And so here we go. Those are the two very fundamental formula to calculate the x and the y coordinates, okay, of any of our points that's given, that started out given in polar coordinates. And then in that way, now it's not too trivial yet, and I can only explain here through the picture, but we will see that better as we go through the actual examples. But the radius itself, anytime we draw a triangle, anytime we actually draw down the x coordinates and y coordinates in rectangular coordinate system, then the radius is always acting as the hypotenuse of a right triangle. So right triangle right here, right angle, 90-degree angle is right here. So opposites adjacent, and this is hypotenuse. And so we've learned from even elementary geometry, this is now really from geometry, that according to Pythagorean theorem, r squared equals x squared plus y squared. We know that from geometry. And I did this a little earlier, okay, in our beginning work as well. And so now, generally speaking, the r, we're going to take that. Technically, it's a plus and minus again, but the physical r, the actual distance, is a positive square root, so it's positive x squared plus y squared. But that is also the third formula, quite important as well, that relates between the x and y coordinate systems and the r value right there. So these are the three important ones that that's a lot of time help us convert interchangeably between polar coordinates and rectangular coordinates and vice versa. Okay, and so now there will be more, but we will get to that later. But so before I head out to any formal example, let's now look at that x equals cosine theta and then y equals cosine theta, and let's try to have some understanding of the reason why back on decimals, even though I was saying that I use decimal to do polar plot, but that's due to some limitation of decimals. I have to do the following. Okay, so now let's look back at the command line right here. See, this is our angle theta. So at whatever angle theta, x coordinate. So in the end, decimal doesn't really have a feature that can directly plot a point that's given in r comma theta. And so we have to do that trick by just putting that in the actual rectangular coordinates. So this is the actual rectangular coordinates, but the rectangular coordinates here came out from our understanding of the radius and the angle theta. Okay, so that's why, see, x coordinates is r times cosine theta. And here on decimals, here I said earlier, we stay away from the actual theta because it's reserved for other purpose. So here is r times cosine t, and then comma r times sine of t. That is what's consistent. This is the y coordinates, this is the x coordinates, and that's making it consistent with what I have just delivered here. All right, and so in that way, now you have a little bit more of a solid understanding of how you can construct your own activity on decimals to help you do the plotting points easily. Okay, and so now at this point, let's get into another example. So we're now at example 2, where we're going to start utilizing this understanding right here. All right, so now I'm going to spend some time writing down the wording of the problem. So in example 2, I'm going to say that the instruction of the problem is as following. Plot each point, okay, with its given polar coordinates. And find the Cartesian, okay, and find the Cartesian coordinates of the points. Of the points. Okay, so go ahead and spend some time to read the instruction of this problem. Okay, so you can always pause the video and read the instruction carefully. But so in the way how I see this instruction of the example, it's asking us to do two things. So first thing, any point that I'm about to give here, or any point that the example is about to give, it's given in polar coordinates, and our first responsibility is to plot each point given. That's what it is for now. Okay, and then once we plot, and at this point I have shown the decimal skills in the earlier example 1. So now feel free to, on your own, try right there, as if you're working through the example on your own, that along with what I'm doing here, then feel free to use decimals, right? And I'm also going to hop back and forth between the board here and decimals, okay, to show the graph and do the calculation. Okay, and so now, but first thing, we have to plot the point, okay, using its given polar coordinates information. And then once we have done plotting it, now we're going to try to find the Cartesian coordinates. Now, so big word again, but I mentioned this earlier in the beginning of our video lecture. Cartesian coordinate is just another name, another way of saying rectangular coordinates. Okay, so now let's look at the first point. All right, so the first point given here is 2, pi over 3. It's a point that's given in polar coordinates. Okay, it's represented in polar coordinates. So this point makes a radius 2 from the pole. Okay, and at angle opening up at positive pi over 3. Okay, so now let's immediately head over to decimals to see this quick sketch of that, to see the quick draw of that. All right. So here's my empty decimals, and you have seen decimals quite a few times. So allow me to just use the closed version right here. So as far as sketching it, and anyone, if you're not ready to use decimals, yes, feel free to copy this picture on your hand sketch version as well, because the idea now I'm doing this now is tentatively, it's also appropriate for those who are working with hand sketch graph like that. Okay, so what I'm doing, if we're doing this by hand, I'm going to look for the angle pi over 3. All right, so pi over 3 is this angle right here, and then I'm expecting a radius 2 on this terminal side. So radius 2 coming out from the pole, radius 2 is about here. So I am expecting that point to be right here. All right, so let's find out. Now the point is on, and yes, that's the point right there. And now just like that, if you really are about to use decimals for doing this, then we just simply change this radius quantity, right? Double click, highlight that and change that to a value 2, and then type the value here, t equals for angle, whatever angle that was. So pi over 3 is what we type, and then with this formula already set up, it will automatically popped out at that point right there. At angle pi over 3, we have that point being 2 pi over 3 right here. The point that made the radius 2 at angle pi over 3. Okay, so now we have already plotted the point. So we got the point. So on back to this board space right here, I am going to do the next part. So the first part here, plotting the point, is done. Now I'm going to find the Cartesian coordinates. So this is that point right here. We want to know what's the x coordinates and what's the y coordinates. All right, and so here's how I'm doing it. And so you got to always remind yourself in polar coordinates, then this is radius. First number is radius. Second number is the angle. Okay, so in that way, we've learned right before we got into example 2 that x, okay, equals radius times cosine of theta. And so in that way, it's quite ready. Radius is given to be 2. Theta is given to be pi over 3, positive pi over 3. And so with this formula over here, x has to equal 2 times cosine of pi over 3. And this is a problem that's very easy for anyone who has learned math past trigonometry. So cosine of pi over 3 is a 1/2, but times 2, okay. All right, and so the answer here is simply going to be 1. So x equals 1. That's how I find the x coordinates. Actually, I shouldn't put that in a box right there. And then similarly, we are going to find a y value. Okay, so y equal okay, from what we learned previously, from what we learned right before getting into this example. Then r times sine theta, okay, and that gives me radius 2, is from that, and then times sine of pi over 3. And yes, another very easy problem for students who have already learned past trigonometry. And so this is 2 times sine of pi over 3 from the unit circle. It's going to be a square root of 3 over 2. All right, and so I highly recommend anyone viewing this lesson right here, learning from this lecture, to review intensively, review your understanding in trigonometry, okay, because a lot of those will keep coming throughout our entire discussions about the polar coordinates right here. Okay, and so now in this way right here, then it's going to be just so y coordinates of our point is a positive square root of 3 right here. So now we are ready. The actual point now in Cartesian, okay. So now I'm going to use double arrow. It doesn't mean equal, okay? It's just a different way of representing it. So from polar coordinates, Cartesian coordinates, I'm going to say it's 1 for x, square root of 3 for y. And that's how we did that. Okay, 1 for x, square root of 3 for y. So now let me switch back to decimals again to just confirm, to double confirm our result right here, our calculation result. So 1 for x and square root of 3 for y. Okay, so that's the point, that point's right here. Okay, 1 for x. All right. Let me zoom it in so that we can show the scales a little more. See, 1 on the x-axis. See, these are still the axis. So 1 for x hits right into the, and let me also switch back to coordinate, rectangular coordinates. All right, see, 1 for x, and that same scale remains here, and the two axes are still here. The same point is still there. It's not being placed anywhere. The poles is all there now. It's just, instead of being in the polar coordinates, we are in rectangular coordinates. So 1 for x, and this height right here is about square root of 3 right there. And that's how it is. Okay. And I'm switching back to polar coordinates. All right, so now we have confirmed, and once again, those are the two formulas that getting us from polar representations over to rectangular coordinates representation. Okay, so now let's get ready for part B of the example, and now we can start speeding up the process. We can start picking up pace here. Okay, so all right, so for part B, it's just another point. We're going to try to plot the point first, and then we're going to try to calculate the Cartesian coordinates of that. Okay, minus 4 is the radius, 3 pi over 4. Minus 4 for radius, and 3 pi at angle 3 pi over 4. All right, so let's now look at decimals here. So with the graph right here, to plot it, I'm going to look for the angle 3 pi over 4. So the angle 3 pi over 4 is about right here. This is the angle 3 pi over 4. And decimal is not showing the label for that, but it's okay. Okay, so 3 pi over 4 is this angle. All right. And now on that angle, I'm going to look for radius negative 4. So that means instead of getting the point on this end right here, I'm going to actually need to put a point on the opposite side of the same ray right there. So on this terminal side of our angle, we're going to put the point on the opposite terminal side, which is down here somewhere. All right, so now let's see if machine is going to agree with what we're expecting. That's where it is, right there. So now that's the point now. We're putting it. Okay, I had to put in some further zoom right there. So radius 4, this is 2, and this is 4. And the angle was supposedly was originally 3 pi over 4, which is this angle. And then we have to put the point on the opposite end of that, and that's how it is. And then in the version of the browser, where you can actually sort of like a further zoom right there to show how you can actually do this with with decimals. I'm going to change that to negative 4. Okay, and then this angle here, 3 pi over 4. All right, so now the point is popped out right here. It's being located right there. All right, and so now that's the point that we're seeing right there. And so now with the point already seen in the plot right there, so if any of you is doing this problem here as a handwritten problem, then you can just use decimals and then make a copy of your graph somewhere in your paper, in case you're working with your teacher who's still maintaining a traditional handwritten submission. Okay, all right. So now, but in the end, the next step right here, x coordinates must be found by r times cosine theta. Okay, so r is -4. Just nothing needs to be changed. Just that exact formula, -4. I'm going to multiply with cosine of the angle 3 pi over 4. And this is the calculation. And again, this is a problem that's very easy for anyone who has already learned past the trigonometry. So cosine of 3 pi over 4 is a negative square root 2 over 2. That's for cosine, and we're going to multiply with -4. Okay, and so the -4 will cancel, and the negative signs will also cancel each other right here. So it's going to become, and the 4 will cancel with 2, so it become a positive 2 square root 2. So we got the x coordinates for our point right here. And now let's calculate the y coordinates. So y equals r times sine of theta. All right, and that gives me -4 times sine of 3 pi over 4. Okay, and you have seen that in the picture earlier, so now it's making it even easier to calculate any of this. So sine of 3 pi over 4 is a positive square root 2 over 2. But now we're multiplying that with a negative, okay, with a -4. So -4 cancel with 2 here. It leaves me a negative, I should have left enough space for myself to write negative, but -2 square root of 2. So this is our y value. Okay, so that means this point right here, currently in polar coordinates, can be expressed in rectangular coordinates as 2 comma square root 2. I mean 2 square root 2 comma -2 square root 2. This is, ladies and gentlemen, that's the same point now expressed in rectangular coordinates. Okay, and so let's just double confirm with that. So on our browser here, on decimals here, this is the point. Okay, the point is placed right here. Okay, so now with that point, let me switch back to the rectangular coordinates. Okay, see, at least how I see it, it has positive x-axis, I mean x value, and negative y value. And so yes, right here, this much is about positive square root 2, I mean positive 2 square root 2, and down here vertically it's about negative 2 square root 2 right there. Okay, and so that's how we're calculating the rectangular coordinates from a point that's given from in polar coordinates. So let's do a couple more problems. And even though I will also walk through the steps, but for starting with part C and D of the problem, I highly recommend if students of mine or viewers can start doing the problems here independently. Okay, and so part C right here. How about we're given a point 1 comma negative pi over 4. Okay. All right, so on the graphing space right here, we're now going to open up, we're going to now look for the angle, the negative angle. So from the x-axis, I'm going to go negative pi over 4, which is down here, and I'm expecting a radius 1. So radius 1 is going to land me into a point just about right there. Okay, so the angle, look for the angle first. In my personal experience, look for the angle first, and then from there we're going to leave the pole in about that much radius. So now it's a positive 1 radius. So now the point is expected to be here. Let me now put the points, put the actual points on. All right, so now the point is there with the actual graph. All right, and so now let's go ahead and compute, do the actual computation, and I'm going to leave that the other decimals. I'll leave that other decimals demonstration for the viewers to actually do that on your own right there. So x coordinates of this point, r times cosine of theta. This is theta, that's r. So now we're looking at 1, okay, that's for radius, times cosine of minus pi over 4. Okay, so negative pi over 4 has cosine value being positive square root 2 over 2. We're multiplying that with 1. Okay, so the answer here is square root 2 over 2. That's our x coordinates for this point right here. Y coordinates has to be r times sine of negative pi over 4. And that is going to be, now radius 1 again, 1 times sine of negative pi over 4. All right, and that will give me 1 times negative square root 2 over 2. And now the y value here turns out to be negative square root 2 over 2. All right, and so in that way, the actual point here turns out to be square root 2 over 2 comma negative square root 2 over 2. All right, so here we have that point written in rectangular coordinates, and that's the point we're looking at. Okay, we have seen the graph earlier, and now we have calculated the actual rectangular coordinates of that point. Okay, so one more time, I'm going to switch back to my browser and switch that to rectangular coordinates, and we can see that yes, this is right about, on the x-axis, it's right about positive square root 2 over 2, and this vertical distance here is right about negative square root 2 over 2 like that. All right. And now one last problem in this particular example. All right, so here part D of the example, we're looking at that point given as about minus 5 comma negative pi over 6. Okay, minus 5 comma negative pi over 6. Okay, so now I'm looking at, let's plot the point right here. Let's plot the point. Okay, so the point here is, again, it's that this point is given in rectangular coordinates. I mean polar coordinates. The point here is given in polar coordinates, and let's look at the plot right here. All right, so with the empty graph right here. Now, angle being negative pi over 6. So negative pi over 6 is about right here. Okay, negative pi over 6. But if it was a positive radius, then we would place the point somewhere in this quadrant. But now at negative pi over 6, the radius itself was negative 5. So I'm going to need to place a point on the opposite end of that. So with this terminal ray right here, I'm going to put the point somewhere out here. So negative 5 is about right there. That's where I'm expecting it. Okay, so now I'm going to actually put the actual points on. I miscalculated I mistyped my decimal. It's negative pi over 6, not 5 pi over 6. Okay, so that's the point where we had it there. Okay, all right, so the point is just right there. It's already successfully plotted. Okay, so now after plotting that, we're going to get back to the board and do the calculation for the rectangular coordinates. So here I'm looking at x equals r times cosine of theta. That is going to give me negative 5 for r times cosine of negative pi over 6. Okay, and cosine of negative pi over 6 is going to be the same as positive square root 3 over 2. Okay, so in the end we're looking at a, okay, I realized I wrote this a little too big. So minus 5 times positive square root 3 over 2. So here we're looking at negative 5 square root 3 over 2. That's the x coordinates, and actually I don't think I need to put this in a box because that's not our final answer yet. Okay, that's just the final answer for the x coordinates. All right, and now we're going to find the y coordinates. So here we're looking at r times sine theta, which equals negative 5 times sine of negative pi over 6. Okay, but negative sine of negative pi over 6 is going to give me a negative 1/2. So here I'm looking at altogether a positive 5/2 for y value. Okay, so now our final concluded point, that same point here originally or initially expressed, represented in rectangular coordinates, I mean in polar coordinates. So now it is going to be minus 5 square root 3 over 2 comma 5 over 2. All right, and now we can put that answer in a box right here, and it's a coordinates pair like that. All right, so that's how we do example 2 like that. We plot each point, okay, and so everybody can have more opportunities to learn plotting these points, and then we're going to convert the points from the given polar coordinates here to Cartesian coordinates, or that's just a formal name, I mean the more fancy name for the rectangular coordinates. Okay, and so now still along this way, let me take you into the third example, even a slightly more higher class, okay, a slightly higher class, I mean a slightly different class of problems like that. Okay, so we're going to call that example 3, and I'm going to erase these points right here. All right, so in example 3, we want to plot each point with its given Cartesian. Okay. So we have each point is given in Cartesian coordinates. And then we're going to find the actual polar coordinates of the points like that. But then here I have to add in some extra understanding right here. I mean some extra clue right here. I want to only express, because polar coordinates has quite a few different ways. I mean in polar coordinates we have, for each point we have quite a few different ways to represent. So I want to write it in a way that r is positive. We express r as a positive r, and theta is also a positive. Okay, and theta is positive in degrees instead of being in radians. Because in the end, when it gets to this, we do need a calculator. To get things work. Okay, and so now, and along the way right here, I am going to show some extra understanding from what we have already learned, so that it will assist into the problem right here. Okay, but so keep in mind, any point given here, any points about to be given here, it has to be it's a point given in rectangular coordinates. Okay, so now this time I don't think I need to switch over to decimals, because it's not that flexible to use decimals here to switch between the two. And so now the first point here is a point at 1, 3. This is x, this is y, this is x, this is y. Okay, 1, 3. So now 1, 3, to plot that as a hand sketch, it's a point that completely stays on the first quadrant. Okay, and so 1, 3, it's about right here. Allow me, if I'm upscale a little bit, 1, 3. So now we plot it, nice and easy. So the angle, so now if we're trying to convert this into angle theta, I mean into polar coordinates, then the angle needs to be the positive angle. So we want to look at the angle in this positive rotation direction like that. Okay, so that's theta, and we want, once we've had the angle being positive, we want the positive radius as well. So those are the two requirements like that. Okay, so that's one thing to keep in mind. All right, so here's what we're doing. Here's how we're doing it. So radius, we can always calculate that based directly on the two coordinates right here. The x and y coordinates, right from your rectangular coordinates, we can always calculate the radius. So from what we learned, from what I wrote down and explained previously, before we got into example 2 and 3 right here, then radius can always be found, okay, as square root of x squared plus y squared. That's what it is. Okay, so now in that way, we already had our two x and y values here. So square root, now consequently I'm going to have square root of 1 all squared plus 3 all squared, all of that is inside the square root. All right, so that means here we're looking at radius being square root of 10, because 1 for 1 square and 9 for 3 square. So together it's square root of 10. And I don't think we can reduce this at all. So we now have radius, okay, as a square root like that. And so now, once again, from our understanding previously, x coordinates must be radius times cosine of theta. And now this is the part where I need to explain, where I did not explain that earlier, and now it's time, it's the right place and the right time to put that in right here. So let me swing over to the other board. All right, so from past trigonometry understanding again, any point in rectangular coordinates or in Cartesian coordinates, y coordinates is here, x coordinates is here. This is x, this is y. So in a triangular system, in a triangular setup like this, okay, then the angle theta can be found by doing. So theta can be found by doing. Because we don't want to go through we just want to use directly our two values that are currently available. So there's a faster reach right here. There's a direct reach. Okay, we're gonna go with tangent inverse of y over x. That is going to give us how much angle that is. Okay, simply because from past understanding in trigonometry, then tangent of theta will always equals to y over x. That's how it is. Okay, tangent theta is y over x. And so in that way, it led to that statement I said earlier. So to find theta, we just simply do the tangent inverse operation on your ratio of y over x. And it will get you the angle. But then there's some extra treatments that we have to apply on top of that. So here's the thing. Recall again from the trigonometry that tangent inverse only give an output as an angle anywhere. So the angle as the output here is only anywhere between negative pi over 2 to pi over 2. So if you're using any calculator, either you're in degrees mode or radians mode, your angle theta that came out from an inverse tangent function will only be generated inside of this interval over here. It's the way it is. It's worldwide accepted. Okay, that's why it's the engineers out there, they program that into the calculator. But then when we're actually working with these problems, there are angles that being outside of that zone, like say an angle like that. So we have to know how to make some treatments right here. Okay, so allow me to actually get that through the example instead of just say everything here in one thing like that. So in each example, it has its own specialty. Okay, so now just keep in mind one thing. The main focus here is to use a tangent inverse. Okay, all right, so now here's what I'm seeing. So now I'm going to calculate theta. Okay, and I am going to go with theta in degrees. I'm going to go with theta in degrees. So in that way, I am going to do tangent inverse of, according to that formula I wrote up on the other board earlier, y over x. So y over x here is going to be 3 over 1. So now I'm going to run the tangent inverse operation. Okay, so tangent inverse of 3 all right, so according to my calculation, tangent inverse of 3, and you can use that with any calculator, any standard calculator, is going to be in degrees. In degrees is going to be about 71.37 if I round it to 2 decimal places. And so rounding, how far to round, it all depends on each problem that you're working with. Every problem has a rounding requirement, so watch for your rounding requirements on each problem you're doing. But so right now, tangent inverse of 3 over 1, y value over x value gives me this angle right here, and it's a positive angle immediately. I mean, it makes sense perfectly because our points, in the way how it's given, it's right in quadrant 1. Okay, and so as a positive angle, it's going that way. So 71.37 degrees right here. It's that angle. So this is now we're done. This is the angle theta. That meets our requirements. We want the angle theta is a positive angle, and then in degrees. So nothing needs to be treated here. Okay, so in that way, that means our polar representation. Same point, but polar representation. Polar coordinates representation is square root 10 for radius, and it's already a positive square root 10. Okay, comma 71.37 degrees. All right, that is the representation of the same point in polar coordinates. All right, ladies and gentlemen, that's how it is. And so plotting this point is easy, so that I don't even want to, because I haven't prepared that with decimals here, but plotting this point should be easy for anyone. So putting that on the screen, on the hand sketch right here should be having no problem for us. So we plot the problem, the points, and then the more challenging part is to get the radius and the angle theta, like that. But the two key things that I need to highlight, we will calculate the radius by using just this formula over here that utilizes directly the two x and y coordinates of our points, and then we go with theta. We go with tangent inverse of theta. Now, there will be students and viewers of my question me that once we have radius here, why not using? Let me switch to the other board right here. Why are we using tangent inverse? We could have also used so because x equals r times cosine theta. And once we found theta and we already know our x coordinates, why don't we go to x over r equals cosine and use a cosine inverse of x over r for our theta? You are more than welcome to try it. I don't want to make that as, hey, because I'm saying this, I want you to experience this on your own to see. I'm not saying that it's impossible. I'm not saying that. I'm not saying that it won't give you a result, but it's going to be a lot more work around than using this route right here. I want you to experience this. I want you to experiment this. So why don't you, on your own papers and pencil, on your own time, try this route right here. You will get to the same result, but it's going to take a lot more work around. Because be careful with the cosine inverse zone, the cosine inverse output range right there. Somebody else can also question me. Since y equals r times sine theta. Okay, why didn't I go with y over r equals sine of theta? And so consequently, we can find theta by doing sine inverse operation of y over r. Again, I am not saying that this route is not giving you the answer. I'm not saying that, but I want you to try it on your own to experiment. The reason why many generations of mathematicians and teachers, including me, have been staying with tangent, okay? Because this will produce more workaround right there. But I want you, if you raise that question in your mind and you are on your way, who knows, to become a formal mathematician, experiment that for your own to learn better experience. Okay, sometimes it's better that you learn on your own rather than just keep having someone telling you. Okay, so experiments with both of these two cases here. What's the cost for using the cosine inverse, or what's the cost for using sine inverse? They're both going to get you the correct answer, but it's going to take a lot more work around. It's not like a simple one calculator button and it gets you the answer. Okay, and so doing this tangent inverse will be the shortest route right here. I'm just saying it's the shortest route. I'm not saying it's the only direct route, but it's at least it's the shortest route. It's a little more direct than these two right there. And I want you to see more closely of why it's not a good choice. Okay? And so the reason I was explaining that, so now back into the highlighted steps. So anytime we're converting between rectangular coordinates to polar coordinates, getting r is a matter of using that formula. And then getting theta, the highlighted step is to use a tangent inverse of y over x. Tangent inverse of y over x. That's get you theta. But hold it, it's not simply just tangent inverse of y over x all the time. So in this problem right here, make another big note for me. The point we are given is in quadrant 1, is in Q1. Okay, many instructors, many math professors and instructors and mathematicians use a Q1 symbol to indicate quadrant 1. Our points, in a way it was given, makes perfect sense to be in quadrant 1. Okay, and so let's step over to another one, another point given. All right, so now we are at part B right here, our given points here. Once again, each point is given in rectangular coordinates or Cartesian coordinates. And the point here is at -3, 1. -3, 1. So as a plot, I don't even think we need to switch over to decimals, okay, because it takes more time to prepare for that. So overusing technology is not always a good thing, you know, even though I'm very into technology. -3, 1. So how about a point right there, -3, 1, okay, and allow me, and forgive me for being a little bit off scale right there, but that's not the point. We're not competing with any machine. Okay, so that's the point right there. It will make some radius, okay, and the point here is -3, 1 in rectangular coordinates. So we got the point plotted successfully. Easy. So now radius, another easy one, and we use this formula to obtain the positive radius. So r equals -3 r squared. You have seen the formula in the earlier part, so allow me to get straight into using that formula, plus 1 r squared. Okay, and that gives me a square root of 10 again. Okay, so r equals square root of x squared plus y squared, and x squared in this case is -3 r squared. Y squared is 1 r squared. And that's how I ended up with square root 10, an irreducible root. Let's leave it the way like that. Okay, so that's simple for radius, and we already had the radius as a positive expression. That's a good thing. That's a good check right here. Now the next step is to calculate the angle theta. So I'm going to go with tangent inverse, just as start. Just go with that. Y over x, so tangent inverse of y over x, so it's going to be 1 over -3, which is tangent inverse of a -1/3, okay? All right, so let's do the raw calculation here. Let's do the raw calculation here. All right, so with my, and so I shouldn't put equal sign yet, okay, because there's more to that. So here's the thing, if we simply just run tangent inverse, if we just simply run tangent inverse on -1/3 right here, this is what's going to happen. Remember, I explained earlier, tangent inverse is only going to give you an angle theta output anywhere between -π/2 and π/2, which is anywhere between -90 degree to 90 degree. Okay, so it can give you negative angle. All right. And so the calculator I used, and pretty much the same with any calculator. You can use that with the TI-83, 84, any standard HP graphing calculator, or the Casio one. It's giving me in degrees, -18.43 degrees. -18.43 degrees. Does this seem to be even correct with our points being placed right here? Okay, in the way how the point is already plotted, the angle we desire, think about it, the angle we desire is this angle. We want that to be a positive angle. This, okay, we want this to be a positive angle. And it looks larger than 90 degrees, agree? You can see it right here through the picture. But now look at our result here. If we simply ran the tangent inverse on -1/3 here, we ended up with a negative. And look at the magnitude of the angle itself. Ignoring the sign, it's only an 18 something, pretty small. So that doesn't look quite right. It seems like it gives us this value right here. If that straight line goes straight down here, then negative 18.43 degrees is about how much angle that is. But that's not the one we're looking for. The one we're looking for is in this picture, it looks like it's the exact opposite end of that. All right, so now to get the exact answer, so now we do this trick anytime that, so now it's time to formalize that. Our point, we notice, unlike part A, our point here is in quadrant 2. So this is the trick we will do anytime that we're trying to find a polar coordinate representation when our point was already plotted in quadrant 2. After plotted, our point is in quadrant 2. And we have to add from where our negative angle is, because it's just the way it's. So to find theta, we have to run, yes, we're still going to run the tangent inverse, but we need to add 180. Because from here to there, it's 180 degrees away. 180 degrees away. Okay, we add 180 degrees. So now I'm going to add 180 from that. Okay, and now I'm going to need to swing by my calculator again to get the exact calculation. All right, so now in precise value, I mean in 2 decimal places, right? But in degrees right here, and precise to 2 decimal places. And here I'm looking at 161.57 degrees. That is our final answer. That is our final answer that looks consistent with the way how the picture is looking. So, because from the positive x-axis down to there, it looks like an angle larger than 90 degrees, because 90 degrees is here. So larger than 90 degrees, it's in quadrant 2. So 161 now makes sense. All right, so now as a final conclusion, the point that we're looking at now, allow me to erase all these extra work right here because I need some space to write in the actual points. So it's, the answer here is 161.57 degrees. So now the final point in polar coordinates, the same point but represented in polar coordinates, is going to be radius square root 10, and at making an angle 161.57 degrees with the x-axis. That's the polar coordinates representation of the same point right there. Satisfying all these requirements, radius is positive, angle is also a positive angle, and it's in degrees. Okay, so that's how we're doing it. So now I was only able to introduce this little trick right here at 180 degrees. So the main central theme, the main central key to get to the angle is still to run through the tangent inverse, but we have to apply this treatment, adding 180 degrees anytime your angle is in, anytime your plotted point is in quadrant 2. Quadrant 2. All right, so that's one problem. Okay, one more problem down, right, after part A right there. So let's look into another one. So you can probably start seeing where I'm going in this. All right, so now let's look at part C of our example. We are given another point right here. How about -2, -4? Okay, -2, -4. And so, as far as the plot, in rectangular coordinates, okay, and it's easily can be seen that -2 is here, okay, then -4 is down. All right, so that's -2. All right, so -2, -4. That's our point, and we have our so the angle theta needs to be this way, and r is that much length made from the pole out to that point right there. So to calculate the radius, then once again it's going to be square root of x squared plus y squared, which is with value substituted in -2 all squared plus -4 all squared. Okay, and that is square root of 20 after the calculation. And then I prefer here to simplify this root, to reduce this root. But if you're learning with any instructor other than me, watch for your instructor's requirements about whether you're going to have to simplify roots or not. If you're studying with me right here, it also depends on problems. So some problems I ask you, and I will put notes on each problem, but some problem I will ask you to reduce roots. Some other problems I ask you not to reduce. So watch for my the particular instruction on whether to reduce root or not. So, but that's radius, 2 square root 5. All right, so now we're going to calculate the angle. So angle theta, just the starting step again, is to find tangent inverse of y over x. So minus 4 y over x minus 2, which is the same as tangent inverse of positive 2. Tangent inverse of positive 2. Okay, so I'm going to leave a pretty big space right here. And we notice, before I get into any further, before I actually get to the calculation, we notice that the angle down here is somewhere in quadrant 3. The angle that we're drawing here, I mean the point we plotted is in quadrant 3, so the angle should be somewhere between 180 and 270 right here. Third quadrant. Okay, so let's look at what the calculator says right here for our tangent inverse results. But this is what we're typing in. So the calculator, all right, so the calculator gave me a tangent inverse of positive 2, which is what this is. Gives me only a 63.43 degrees. 63.43 degrees. I mean, it's as far as the two requirements for angles being a positive angle, this answer here passed that requirements, but as far as being the actual magnitude, it didn't pass, because look at our angle, look at our plotted point. So it's at this point you can see that it's extremely important that you know how to plot these points. So it drives. So successfully seeing the picture will drive your decision on doing tangent inverse here slightly differently in every problem. Okay, so 63.43 is only about somewhere here, is only about some point here in quadrant 1. But from quadrant 1 down to quadrant 3, what do we need here? We need to actually, it looks like in the picture here, it needs like, the answer here is 180 degrees away, right? Add it on top of what we found. So 63.43 is about right here. But our answer, our angle we actually need is down here in quadrant 3. So in that way, so now another trick that we picked up here. Anytime we're calculating the angle theta for a point, we want to treat it as a positive angle theta, and the point is plotted in quadrant 3. Then the treatment we have to do is we're going to add 180 degrees. Okay, 180 degrees to our answer that came out from tangent inverse. So just like what we did in part 2 right there. I mean in part C, in part B of the current example. And so now in that way, I'm going to go back to this answer, and we have to adjust that. All right, so 63.43, but added with 180 right here. We are now looking at 243 degrees. Okay, point 43. All right, so that is your angle theta. So now your points that initially represented in rectangular coordinates here is now ready for polar coordinates. We're looking at 2 square root of 5 as the radius, and the angle here is 243 degrees in positive angle. And that's our point here in polar representation, polar coordinates representation. Okay, so this is the specific trick when your angle is in quadrant 3 here, and we specifically use the tangent inverse function. Okay, and so now let's look at the fourth example. And you can start seeing where I'm going with this. I mean, you can already start seeing where I'm going with that since the end of part B already. And so now, when we're looking at part D, the point we're given here is 1 comma negative 3. Okay, and so now plotting out this point, 1 comma negative 3, we have a point about down here. Okay, this is where 1 comma negative 3 is. That's rectangular representation of that Cartesian coordinates. All right, and so now the angle, if we would draw that, is going to have to be this angle in positive direction. Okay, and then this is R right here. All right, so now again to calculate R equals square root of x squared plus y squared. And then so here I'm doing square root of 1 all squared plus negative 3 all squared. All of that is inside the square root. And so I'm looking at specifically square root of 10. This is my radius for that. All right, and so now let's get there with the angle theta. So I'm going to start out with that tangent inverse step right here. Tangent inverse of y over x. So y is negative 3 over x is 1. So negative 3 over 1. Okay, which is the same as tangent inverse of 3. Okay, tangent inverse of 3. And so now I'm going to leave a little bit of space here. I want to leave a little bit of space right here, and let's write down the answer, and we're going to make some decision. Okay, so this is tangent inverse of negative 3 actually. All right, tangent inverse of negative 3. So the answer came out for me was a negative 71.57 degrees. Negative 71.57 degrees. So it looks like the answer here failed the requirements in the sense that we want positive angle. Okay, but as far as the magnitude, it actually does reflect the angle here. But if we're looking at that as a negative angle, it's the way how tangent inverse is. Okay, so now the treatment we need to apply here, notice the answer here is that angle. This is negative 71.57 degrees. Okay, and then we notice our point right here is in Q4. So this is the trick that once we picked it up, it will be the general trick for any time we're getting the angle theta in degrees, right, as a positive angle in quadrant 4 here. I am going to see this actual point, but now seeing as a negative angle. But if you want to see that as a positive angle, we're simply going to add 360 degrees to that tangent inverse. So I'm going to add 360. Okay, and so now in that way, allow me to add that on the computer. Okay, so the final answer of mine came out instead of a negative answer, now we're looking at a positive answer. Positive 288.43 degrees. And this is the final answer for that angle right there. Okay, I shouldn't even put that in a box right there because it's not really just our final answer. It's just part of our final answer only. Okay, but now at least this angle makes sense with where we place that in Q4 right there. All right, so now the final polar coordinate representation of this same point is going to be square root 10, it's being the radius, and 288.43 degrees, right, in positive direction. That is our polar coordinate representation for this same point. All right, and that is the entire intention of that the example number 3 right here. So what we picked up from this is a couple of special rule that when you run the tangent inverse, so the key here to get angle is we're always going to run tangent inverse instead of running the sine inverse or cosine inverse, because it's easier here. It's just easier here, less work here. But we're still going to have to apply some treatment. So when you view these lessons right here, you can always roll back to the lesson and pay attention to the part where I highlight in red right here. So I wrote in red that quadrant 4, I wrote it in red to catch your attention. Then we have to apply that treatment that correspondingly I wrote in red. That's how it's done. Okay, and we need to see the plot, and that's why the problem asked us to plot each point first. And once we have a visualization of the point, we're going to be able to decide what treatment we're going to need, right, appropriately for running the tangent inverse. It's just the fault of these tangent inverse or sine inverse or cosine inverse. It has a limitation with those, so we have to apply the correct treatment in that. All right.